Good afternoon, ladies and gentlemen. Welcome to our lesson on Unit 7, Differential Equations in the AP Calculus curriculum. I am John Allison. I'll be your consultant today, and we're going to start with a video to kind of motivate you, get you to see what real life applications there are out there. Some of these are a little beyond the scope of this class. They'll go into farther classes that you'll take later, but if you're going to do, what you're going to see in this video is if you're going to do anything in life that's heavily involved in math, you're going to find differential equations are a part of that. So let's get started with the video. It's a little bit longer than I'd like, but we'll try to cut it back a little bit and kind of trim it down. And so you'll see lots of applications for differential equations in almost any field you go into that's heavy in math. There are economic applications, there are scientific, biological, chemistry, it's everywhere. So I want you to see how important it is that we learn about differential equations and understand differential equations. The next thing we're going to do is we're going to look at a few little short problems, just a review of differential equations really quick, just the general idea. We got a basic general differential equation, which just means that we have a function that involves its derivatives of the function's derivatives. Sometimes the function itself will appear in there as a y, and then we'll have the independent variable x appear in there also. So let's look at this simple differential equation, dy dx equals 2x plus 3, and review how we solve these. We just multiply both sides by dx to get dy equals 2x plus 3 times dx. Then we integrate both sides. The integral of dy is y, the integral of dx is x, but the integral of 2x plus 3 dx, which you've already learned, is x squared plus 3x plus some unknown constant, because there's an infinite number of solutions to this equation. This is what we call the general solution to a differential equation. Later on, we'll talk about how to find the particular solution when we know a point on the graph of the solution to a differential equation. So here, I want you to look at this and give it a shot and see if you can find the solution to these 6 really easy differential equations. Remember, when we integrate, we multiply both sides by the differential dx, and then we integrate both sides with respect to their respective variables. I'll give you a few minutes to do that. And if you have any questions, I'll be happy to answer them. We'll see what's wrong, what's right. Give you a few minutes. And once that time is up, we'll go ahead and go over the answers, make sure everybody's good on this. If you don't have an answer, if you got a different answer than what I tell you, then let's talk about it and you ask your questions and I'll go through and help make sure you understand what maybe we went wrong. So on the first one, the answer should be that y equals 1/2 x squared plus 5x plus some constant. The second one, multiply both sides by dx, get dy equals 2x plus 7 times dx, and we would end up getting y equals x squared plus 7x plus the arbitrary constant. These next 4 are things that you should really, by this point, recognize as real easy derivatives of certain functions. The cosine is the derivative of the sine, so when we integrate cosine x dx, you should see that this is going to be y equals sine x plus some arbitrary constant. Everybody knows the derivative of e to the x by now is itself, and therefore the integral of e to the x dx is going to be e to the x. So this one will be y, number 4 will be y equals e to the x plus some constant c. You know that the derivative of ln x is 1 over x. So this one, we got to be a little tricky here, and you should know this already if you've been learning integrals and antiderivatives, but dy dx, when we do this, we'll get dy equals dx over x, and integrate both sides and get y equals, when we integrate dx over x, we can't just leave it at ln, we have to do ln absolute value of x and then plus c. That's one thing I want to point out. We can't forget that absolute value when we do the ln x. Your teacher should talk more about why that is, but that should be the solution to that one is ln absolute value of x plus some arbitrary constant. And of course, the next one is you see the derivative of the inverse tangent there, or the arctangent. So when we integrate this one after we multiply by dx, we get y equals arctangent x and then plus some arbitrary constant. So that's a real quick review of differential equations and how we get them. The next thing I'd like for you to look at is a GeoGebra applet. And I'd like for you to look at this, and I want you to pick a function. I'm going to show you how to do this with a really simple couple of functions. And we're going to, let's dismiss this. I want you to take a function that you know what the graph looks like. Any function. I'm going to use y equals x. And I know that the derivative of y equals x is just 1. And so that means, let's look at this in another way. This let's point this out real quick. The independent variable in this applet is x, and the dependent variable is t. So this is actually going to be the function x of t is what we're solving here, what we're looking for. So I'm going to say the function is x of t equals t is the function that we're taking the derivative of. If the derivative of x with respect to t is 1, if dx or if x of t equals t. So I'm going to plug in that differential equation dx dt equals 1. I know that the graph x of t should be the line y equals x plus some arbitrary constant. So I'm going to look at this and know that the point 0, 1 is on the graph. That means when t is 0, x is 1. So we'll get into that a little bit more later, but I want to show you right now. I'm going to move this down to here. I'll tell you what, let's just swap it right here. You can set the original value in your applet to 0, 0, and then we'll work from there. So if dx dt is 1, and I enter this in here, I'm going to click Show Solution, and it should see the function that is the solution to this, which should be just x equals t, which we all know is a line that cuts the first and third quadrants in half. So when I click this Show the Solution, there you see the line x equals t. We could do another really simple one, like if x was equal to t squared, we would know that the derivative of x with respect to t would be 2 times t. So I'm going to plug in here 2 times t and do the same thing. And remember, this is the derivative of the function x equals t squared, which is just a parabola with its vertex at the origin. So we should see that. And you do. So I'd like for you to pick a function that you know the derivative of. Write that function down. I would have written down x equals t squared. Then take the derivative dx dt. Write that down. So you know what the graph of your function x of t looks like. I want you to enter its derivative in your applet here and play with it and see if it doesn't return you the graph of the function that you started with. So what I want you to see from here is that this differential equation has a solution that is the function itself. The solution to the differential equation, dx dt equals 2t, is the function x equals t squared. And that's what we see here. You play with it for a minute or two, pick out a function, try it. If you have any questions, ask me. If we did, I'm not sure if this will do cosine t or not, but I'm going to try it because I should see the graph of, you know what I should see if this derivative is cosine t. Should see sine t, right? Let's see if it gives it to us. And it does. That's the graph of sine t. What's the, I'm going to let you pick some functions now. This is so much fun. I'm having too much fun trying to have all the fun. I want you guys to have a little fun too. So play with it. If you have any questions, I'll be happy to ask. If you have a function that you don't know or that comes up something you didn't expect, we'll see what we can do and figure out where it went wrong. At this point, I would work any questions or help any questions, answer any questions. One thing you might notice here too is these little marks, and you should have at this point talked about slope fields. And the slope fields are generated by just using the differential equation, picking the x and y value of a point. You should know how to do that and make the little tick marks. But this gives you the slope fields so that if we change, you should see that if we change the point where we started with, the initial point that we had on the graph, 0, 1, this gives us, let's change it to 0, 1. And we see it's the same curve, but it just went through that point. And notice, just follows the point, follows the trajectory of the slope field. So that's what this little applet will help you see. It will show you how the slope fields work. It will show you how the solutions to differential equations appear. And in a few minutes, we get on to show the Euler method approximation. We get to Euler's method. We will show you how that will work on this applet as well. It's really pretty cool. As a matter of fact, speaking of Euler's method, I want to take you to the next little video clip I have for you. This is a clip from a movie that most of you have probably seen. It's called Hidden Figures. It's a great, great story about a group of African American women who were huge, instrumental in the NASA project to orbit, to launch rockets into space and bring them back safely. They were huge in the space program at a time when African Americans weren't really given many opportunities to play important roles in just about anything. And so this is a huge movie, a great movie. If you've never seen it, please do it. But you notice this young lady is the only African American woman in this group of all white men working for NASA and trying to come up with a way to get a spaceship back into the Earth's orbit without it burning up or without it bouncing off the atmosphere and leaving into space forever. The spacecraft has to have a really specific trajectory to come through. And when you listen to what she says, we'll talk about it more at the end. Let's just watch this really short clip. Oops. Let's start play first. Has it hit? So you see, this young lady who passed on the street, nobody would have thought that she could even come close to working for NASA. She solved a problem that none of NASA's top scientists could handle using this method that you're studying right here, Euler's method, which is just an extension or an adaptation of what you learned before, the tangent line approximation. This is just multiple iterations of a tangent line approximation. It's really, really cool. And the little applet that we just used has an Euler's method approximation and shows you how it works. So let's go back to that function that I started with, or one of them that I started with, the function x of t equals t squared. Its derivative was 2t. When I put it in there, it gives me this solution. This time it has the original point at 0, 1, so it's moved up on the x-axis. But if I show the Euler's method approximation, this is going to go to multiple iterations of the tangent line approximation, where we use the calculations of the tangent line, make an equation of a line, and then for the step, what we're going to call the step is the change in the t value here. It's going to calculate the tangent line approximation. Then it's going to go back to the differential equation. It's going to calculate the slope of the curve at that point, the rate of change at that point. It's going to use that to generate a new line, and you'll see. It's going to be great. This is the Euler's method approximation when the step size is 0.5. I'm going to up that a little bit to step size 1 so that you can see more how it really is. So this one goes 1 unit out using the slope of the line and tangent line of the curve here. Then it recalculates for t equals 1, the slope of the tangent line, and it goes one more unit out on that line that goes through this point, the previous approximation. And you can see that the approximation is pretty well off from the curve, which is going to be way up here somewhere. But watch what happens as we move the step size to 0.5. You see how when we get to 2, it's obvious that the curve, the estimate, is a little bit closer than what it was. This at 2.5 or at 2, let's go to 2. The approximation is at 4 when, or sorry, x of t is 4, and here we're looking at something fairly close to 4. Let's even go closer, and let's go to x equals point, or sorry, h equals 0.0, or sorry, 0.25. Making the step size smaller, you see how it gets closer and closer. I'm going to go to 0.1 now. Oops, that's already 0.1. That's 1. Look how close the Euler's method approximation is to the curve. Let's go to 0.01 for step size. You can't even distinguish it from the curve. This is amazing. It's because, and especially with the advent of computers, with computers coming online, and we can make this h almost infinitesimally small, but so small that the approximation can be really, really close, even for values that are far away from the point that we know is on the curve. So Euler's method is super powerful, just like it used to be. If we have a function for a rate, for a change in a change in the value of the function, but we don't have the function itself for a solution. And the truth is, what you should have seen by now is that some functions can't be integrated analytically or algebraically. We have to use computers and numeric methods to come up with approximations. And Euler's method, with computers that can just iterate almost infinitely, we can get really, really close approximations that are close enough to do such things as bring a space capsule back safely to Earth. It's really, really awesome. Awesome stuff. Euler's method, and you see how great it was for a lady who nobody would have ever thought could do such great stuff. Hey, the next thing we're going to do, we're going to look at an actual AP exam problem from 2022, free response question number 5 that was released after the exam, and a guy online has a solution to it. I want you to see how these questions are asked on the AP exam, and I want you to be able to be able to find where to find them and where to find the questions, where to find the scoring rubrics, and see how they're asked and how they apply. It also brings in a few review topics when we do this. First, we'll look at the AP Central College Board.org website, show you where you can find all the released items that they've published. We go to AP Courses and Exams, Course and Exam pages. We'll scroll down since we're doing AP Calculus. You can do AB or BC. Because we're doing differential equations right now, and the AB questions each year are more about the AB questions that are devoted to differential equations are a little more extensive on differential equations. They're tested as a secondary topic on the BC sometimes. I went to the AB exams, and we're going to go to last year's AB exam. Scroll down here. Oops, let's go to the exam first. Oops, the exam. And then we'll scroll down a little ways, and you'll see actually the released problems, free response questions from 2022 right here. And if you click this link, you'll see the scoring guidelines. You can even go over here, see sample responses and how they were scored. You can look at the chief reader's reports, which tells what he saw and deficiencies in trends. So it's just a world of information that can help you do better on the AP exam. And if you really want to do better on the AP exam and get college credit, these are things that you need to practice. So we can go to this. It brings up the 22 released items. Number 5 is the question we're going to look at here. And we've got this guy, looks like Turks Vids. He's going to give us his solution. So that is an example of one of the problems that was on the exam last year. So this, if you need help, this is a great resource. And the calculus exam is structured very similarly every year with similar problems, just asked them a few different ways. But if you start practicing those problems and using those resources that are available to you, it'll greatly help you when you go to take the AP exam. All right, we got one more thing to look at here, and that is a logistic differential equation solver. This one is another GeoGebra applet, and we have a differential equation, a logistic differential equation. It's in a little bit different form than what the the College Board CED uses. I'm going to show you that it's an equivalent form real quick so that you'll understand. L here is the carrying capacity of the population, and K is this growth or decay constant that we're used to using. But if we have this is going to be f of ty, our differential equation. This is just going to be dy dt here. And that's equal to ky times 1 minus y over L, where the differential equation in the College Board CED writes it as k times y times L minus y. So how do we get that equal to what we started with in this applet here? Well, if we multiply by 1 over L here and by L here, we've really multiplied this entire equation, this entire right side by 1. And so we end up with K over L times Y. And we distribute the L inside the parentheses, we get L minus Y. So this K that the College Board is using is just in this template or in this applet is really what they're calling K over L. So these are equivalent forms for just a different K. Uh, Either one is usable. I just want you to understand the difference there and how this applet presents it in a different form. But we look and let's set the carrying capacity at 6 here. And that's just this logistic function cannot grow above 6. It can't get to 6 technically, but depending on where our first starting point is, in this case we've got A at negative 3.64, and that's 3. It's going to show you to the right. I wish it would show you both ways. We can kind of do that by moving B. My B, let's see where B is. Let's make B, but this graph on this template or this applet will only go in one direction. So I thought we could, oh, I guess we had to, let's do it this way. That's really not what I wanted to do. Let's see, my little window here is in the way. So I'm going to try to make it a little smaller, maybe move it around a little bit. It's not the way there. Get rid of the calculator. Let's move our A around a little bit here. And why is this now? Let's move B. And so you can see that that graph behaves logistically. If we go backwards with B, we can see it moving back this way. And so you can tell that the range of this function, as we go toward negative infinity, it approaches 0 but never reaches 0. And when we get to A, we go past A, it approaches the carrying capacity but never reaches it. Interesting thing, one of the things that College Board typically asks you about is what happens at A. And you see it's concave up here. When I cross through A, where that value is really close to 3. In fact, it should be actually at 3. If I change it to 3, you'll see it. But halfway, half of the carrying capacity, when the Y value is half of the carrying capacity, that point on the graph is always going to be a point of inflection where the graph will change concavity. So that's one thing I want you to see. So when you see this in this form, that you know that if you know the carrying capacity, you know when the Y value is half of that carrying capacity, that's the point where the function is going to change concavity. So that's the inflection point. And this is what I want you to play with and see what happens as we change K. It flattens out, or not flatten out, but it makes it less pronounced. Takes longer to get to the carrying capacity. As we increase K, it gets to the carrying capacity quicker. But you can play with this and adjust your carrying capacity and adjust your A. Move A over here. You can adjust your L. You can see that it's limiting your carrying capacity. So I'll let you play with that, see how it works. Just know that when the Y value is half of the carrying capacity, that's when you have a point of inflection. You know, if the range is from 0 to the carrying capacity, and that will help you solve these differential equations. So I hope this has been helpful for you. If you have any questions, I'd be happy to answer them at this point. Right now, we're going to close this lesson out, and good luck to you on the exam and in your future lessons.